Hello? Oh, all right. Hi, everyone. My name is David, and this is Jan. We're super excited today to share with you our Back to Basics hands-on deployment of stateful workloads on Kubernetes workshop. So what we're going to be doing today is first, for about the first 20 minutes, we're going to be covering some basic Kubernetes storage concepts. So those include basic workload concepts, some dynamic provisioning, debugging techniques, and how to use kubectl. And then after that, we'll have a hands-on portion, so that's about 20 minutes in, where you can log in with the accounts given and work with Jan to actually bring up a cluster and bring up some stateful workloads on your own. All right, so before we get started, some general housekeeping. We have some TAs that have positioned themselves around the room who have graciously volunteered their time to help you. So if you have any issues at all, say your internet's not connecting or your cluster's not coming up, you can't find a certain button, whatever problem you have, please raise your hand and look for one of these TAs to help you. Okay, so they're here for your help. Feel free to utilize them however necessary. I'm going to please ask for you to save your more general questions for the end of the talk, so we'll leave time for questions at the end. This is just because, you know, we don't want to slow down, we don't want to bog down the hands-on portion or the concepts for questions in the middle. And one final thing, in the hands-on portion of the tutorial, we just ask for you to not work ahead. We'll have adequate time to cover all of the material. Jan will be going at a fairly comfortable pace, but not super fast. And so Jan will also be covering more information as we go on. So if you work too far ahead, you might not catch like the conceptual information that happens as we're going through the tutorial. All right, so without further ado, some conceptual information. So I want to start by showing you a basic stateful workload. So many of you may already be familiar with kind of the very basic of Kubernetes, which is that it's a container orchestrator, but it's sort of actually a pod orchestrator, where a pod is a collection of containers as well as its configuration information, environment variables, images, some commands. And in our case, actually, it will also contain some storage information, or persistent storage information. So in this example here, our sleepy container has a volume mount, and this is called data. And that's the volume that we're mounting into our container. So here's the path that we're giving it. And you can see that we've actually defined what data is in this pod specification as well. And we've defined it to be a reference to this thing called a persistent volume claim. So you might be wondering, what is that persistent volume claim? Well, we have two main storage objects in Kubernetes, one of which is a persistent volume claim, and one of which is a persistent volume. So first, let me go over the persistent volume claim. So this is a user object. So this is generally created by a user along with their workloads, and it basically represents all of the information that you might need from the workload, like the request for storage that a user will give. So in our example, we have, as a user, I just want a disk, any disk with 5 gigabytes, file system type, and read-write once, right? And the persistent volume, which is kind of on the other side of the equation, is the storage administrator side of the equation. And so this is actually a reference to underlying storage. So this generally has some more information associated with it. In our example here, we have an NFS volume, and so we actually have the IP address of this the underlying disk, right? And so we can find the volume. And what happens actually in Kubernetes is that these objects bind together. So we have the user side, the one that's created by the user, the persistent volume claim, and the persistent volume, and they bind. So here's a quick diagram of kind of how it works in the system. we have an admin pre-provisioning persistent volumes, which reference persistent disks, okay? And when a user comes in and wants to run their workload, they're going to apply their workload YAML to the cluster, so that's their set of containers, which is called a pod. And that references a PVC, which can then bind to the most appropriate persistent volume. So in this case, the persistent volume claim kind of finds the most appropriate persistent volume in the system and binds to it. All right, so that's the basics, and then we have dynamic provisioning. Okay, so to explain dynamic provisioning, we have to explain one more API object, and this is the storage class. And what this is a representation of an entire class of storage. So in our example, we have two example storage classes. One is slow and one is fast. And we can see that they contain some parameters for each, saying whether we're using like standard hard disk drives or solid state drives, right? So we're kind of grouping persistent volumes. And what we can use this storage class to do actually is, here's the image from before. And what we can use the storage class to do here is kind of like the admin creates the storage class, but now no longer has to pre-provision all of their persistent volumes. So what happens is when you create your workload and your persistent volume claim, it's going to reference the storage class, which then Kubernetes knows how to use the storage class and its parameters to actually provision the underlying disk, if you're on a cloud, and generate that persistent volume object that references that disk that we can then bind with. Okay, so what are some of the benefits of dynamic provisioning? Well, we can, one, decrease overhead by only creating the disks that we need when we need them, right? So that's the dynamic part. We group volumes by storage characteristics, so they kind of have a natural grouping there. And we also decrease the burden on the cluster admin so that they're freed up to do other important things. All right, so that's kind of the basics of storage. Now we'll talk a little bit more about higher level workloads. So we actually don't recommend that you use pods by themselves in production workloads, and that's because pods are kind of ephemeral. And what that means is when you schedule it to a node, to a VM, if your node dies for any reason, your pod gets kicked off, right? Or if your pod gets preempted, say another pod with higher priority comes in, your pod gets kicked off, right? And so you kind of lose, you don't have that kind of resilience that you want from a production system. So we have some higher level workload concepts in Kubernetes that can help you, give you some higher level building blocks to build your resilient systems. So one of these is a deployment, and what this does is it just runs many replicas of a single pod template. So the pod that we have before, it just runs like X many of them, right? When a pod is deleted, it replaces it. You can scale these things up and down, right? You don't have to have 3 replicas, you can have 5, you can have 8. But the caveat here is that all pods share the same PVC, okay? So if we look at this image here, it kind of shows how this is working. So all the pods kind of reference one PVC, which means they end up referencing one piece of storage. Right? And this is a pretty big caveat. This means that all of your replicas of your workload are actually writing and reading from the same disk. And some of you may be thinking, like, that's probably not what I want, right? So a lot of times what happens is that these workloads will kind of stomp on each other. Some of them will refuse to start, some of them will crash. Unless you've built your workload specifically to all read and write from the same data volume, this is probably not what you want. So for a little bit more storage-focused higher-level workload, we have what's called a StatefulSet. And that's actually very similar to a deployment in that it runs many replicas of your pod. But the difference here is that each pod gets its own persistent volume claim. And this is generated through a persistent volume claim template. Okay, and Jan will actually talk about this a little bit more later, so we'll see an example of that. But basically what that gets you is that each pod now has its own storage backend, right? It has its own volume. And this may look like it solves all your problems, but actually this has its own caveats too, in that the pods actually, generally in your workload, have to be aware of each other. They have to all be like members and do some leader election. So without that, your replicas don't really know how to interact with each other. Basically, all your pods need to have some method of being aware of each other, doing some active-active or active-passive membership. Okay. One other concept that we need to cover is services. Okay, and so what this is basically defining a logical set of pods. So generally, a service is related to our higher level workloads in that it kind of sits in front of it. And what it does is defines these as one logical set and gives you access to them. So we have a couple different types of services. The standard one kind of being a DNS name for your grouping of pods, as well as an IP address for your grouping of pods, and it load balances between them. So if you hit this IP address, it will load balance between your pods, right? And what we have, kind of a weird name, but the load balancer service, it does all the things that a standard service does, but it also provides you with an external IP. So this allows you to hit that kind of service from outside of your cluster as well. So the standard service is for inside, load balancer is for outside. And we have a third concept called a headless service, which is very similar to a standard service, but it doesn't have that IP and DNS name at the top level. So actually, we're just going to have an IP and DNS for each pod. So we're not kind of aggregating the pods anymore. We're assigning a DNS name to each pod, and that's if you want to kind of direct traffic to pods separately or individually. Okay, so I've explained like a ton of objects, maybe like 6 or 7. What do you do with them? Well, we have this command called kubectl or kubecontrol. I've heard someone called it kubectl or kubectl before. I don't think that's right, so don't call it that. But so here are some useful kubecontrol commands. We have, and these are the ones that we're going to be using later as well. We have apply, right? This just kind of takes your YAML definition and puts it onto your cluster. We have delete, that does the opposite, right? It removes your object from your cluster. You can get a basic list of API objects. You can describe the objects. This one is important. Remember describe. I think a lot of people don't know about it, and it gives you much more information that helps you debug your cluster. You can get logs. You can execute commands directly on your containers. And of course, this is not exhaustive. We have a link here. The slides are online. You can go and find all the rest of the commands as well in your own time. Okay, so before we move on to the hands-on portion, I want to cover a quick debugging technique that can be very helpful in debugging your hands-on cluster, as well as your future Kubernetes stateful workloads. So here in my example, when I do a kubecontrol get pods, I notice that my web server is pending, and I notice that it's pending for a long time. Now, this is something that we don't want. So what I do is I use describe, and I describe the pods. And what this actually gives me is a list of events. So I can see that the pod has failed to schedule because it has an unbound PVC. This is a storage object, as we talked about earlier, right? So now we know kind of where the culprit is. So we go in and we describe our PVCs on the cluster to find out more, right? And when we do that, what we notice is that provisioning failed because the storage class, which we also talked about, is not found, right? So this kind of gets to the root of the issue. It's kind of a contrived example, but we can't find the storage class, so what do? We check the storage classes on the cluster. We notice that there are none, and so we just create this storage class, we describe it. We can see, okay, we've put this storage class on the cluster now. And now, when we actually describe, we wait like a couple seconds, and then we describe our web server, and we note that, it's gotten scheduled, and it's, pulling the images, it's creating things, and it's running now. So what actually happened is we don't need to do anything else besides creating that storage class, because Kubernetes is self-healing, right? Once that storage class exists, the PVC in its loop will eventually find that storage class and heal itself and make everything work and connect to a PV like it's supposed to. And then the pod will then find that PVC and find the underlying storage. We didn't have to touch anything besides resolving the underlying error. Okay? So that's the conceptual part done. And now Jan is going to walk you through the hands-on demo.
Thank you. Well, first we need a Kubernetes cluster. Everybody of you got tiny piece of paper with logging details. So go to this web page, console.cloud.google.com, but please use anonymous windows. Otherwise, it will conflict with your own Google account. So anonymous window in your browser is the best thing to do. And that's actually what I'm going to do. I will open a new anonymous window, console. Oh, what was the? Cloud, Google.com. And I will try my Dev Star 4788 at GCP Lab. Me with super secret password. Sure. Okay. I need to accept Google spying on me and doing whatever they want to do. And I am at my cluster console. Ooh, okay, I need to agree with more. My country of residence is Czech Republic. Do you have it in the list? Come on. Czechia, nice. And I don't want periodic emails. So, this is our Google Cloud Console. We need just a very tiny part of it. We can find under this hamburger icon and Kubernetes engine clusters. Really? Why? Okay. Then I need to pick a project. I will pick this KubeCon stateful tutorial. And it doesn't allow me to create a cluster.
It takes like 1 or 2 minutes.
Okay, we have 2 minutes to create a cluster. Nice. So everybody is on the same page. Everything is working so far. Hello, can we get the mic working?
Hello? Okay, so that API enabling, that only needs to happen the first time you create an account. So in this case, all of you are using new accounts, so they need to enable the API really quickly.
Okay, so everything is fine. I can now create my Kubernetes cluster. And I leave the default. Can I zoom it more? Is this readable? I will pick a special zone, Europe West 1. Where is it? It doesn't really matter which A, B, C, or D I choose B. It doesn't really matter. Just because Google staff confirmed this zone has the right amount of resources, I don't need to configure much. We will get 3 nodes. Let's use 4 CPUs with 15 gigabytes of memory. That's enough. Google pays. And, well, that's it, actually. So just the zone, Europe West 1, 4 CPUs, and create. Now it takes a couple of minutes to create the cluster. Like Google machines are booting up, creating the cluster, joining, starting logging, starting monitoring, everything. It takes a couple of minutes, so let's look at what we are going to do in the hands-on. What's the goal? And the goal is to run a very simple application that will do just a counter. We will show a web page with a counter. Every time you reload the page, the counter bumps. For that, we will start a Cassandra database. We have chosen Cassandra just because it's really easy to set up for this tutorial. We are not database experts. We don't endorse Cassandra in any way, but you will see it has pretty nice features, and it works pretty well in Kubernetes. So that's why we use it. It behaves the way we want it to behave. And the rest of the tutorial will be on this GitHub page, so please open it. It will contain all the commands you need to do, so you can just copy and paste, and everything will work. So please open your web browser, github.com/j/CAAS, counter as a service. That's what we do. That's our business plan, to sell this counter. So everybody has this web page opened? Or you are not paying attention at all? I assume you have it open. So the goal is, again, a StatefulSet with Cassandra cluster. We will have 3 nodes in the cluster, 3 Cassandra pods in the cluster, sorry. And we will have just a tiny deployment with the application, with the web front end that connects to the Cassandra cluster using Cassandra query language. Now, all the pods in Kubernetes have basically random IP addresses. So how can our application find the database if the IP addresses are random? We use the service, we use headless service that provides DNS names to these pods. We use StatefulSets, and one of the benefits of StatefulSet is that it provides stable names for the pod. We will have pod named Cassandra-0, Cassandra-1, and Cassandra-2. Headless service creates DNS entries for us, for these pods. So our application just resolves this DNS and can connect to the database without knowing the IP addresses. And we will create a second service, now with type of load balancer. As David explains, that service will just do load balancing between one pod, so, well, not much useful, but it will expose external IP address we can reach from outside, from the internet. The YAML file for the StatefulSet is pretty long, but as you will create the StatefulSet, you can look at the YAML file. It's well documented, and it's pretty straightforward. Here's just a small excerpt. We will ask for, where is it? We will ask for 3 replicas we ask for 3 pods in the StatefulSet. Here is a template of the pod. So Kubernetes just takes this template and copies it 3 times. Inside the template, we run Cassandra image, whatever it is. And we mount something called Cassandra data into /Cassandra_data inside the pod, inside the container. This Cassandra data refers to a persistent volume claim template. So each pod gets its own persistent volume claim. It will be named Cassandra-data. And we just ask for 1 GB of storage that's readable and writable by single pod. So what Kubernetes will do, we will create the StatefulSet with templates. It will instantiate the templates. We will get 3 pods and 3 persistent volume claims. Now, dynamic provisioning will kick in. Google magic will happen, and it will provision 3 persistent volumes somewhere deep in the Google Cloud. And we will have persistent volumes in our Kubernetes, persistent volume objects in our Kubernetes cluster. And each of them gets bound to our claims. After that, when we have everything set up, Kubernetes will start the pods, and that's where Kubernetes stops. It starts the pods. So we will have 3 different pods. Each of them will have its own Cassandra daemon with its own volume. But if you write something to one of the pods, like here, if you write something here, it will be just stored here. And if we want to read the value from the different pod, it's not written here. So that's not part of Kubernetes, but part of the configuration of the StatefulSet. You must configure the application to join somehow, to form a cluster, so they spread the data and, I don't know, do some redirection or active-active, whatever you want. But this is not part of Kubernetes. Kubernetes will not do that for you. That's your job. In Cassandra case, it's super simple. So by now, our cluster should be ready. Everybody has working cluster, nice and running with green icon, right? So let's do some command line interaction. You press the connect button, and you run this magic command in a Cloud Shell. What? What's this? I never had it. I never saw it. Anyway, we start Cloud Shell. What happens? Somewhere in Google Cloud, a new VM is born. And is it starting? And it will start a shell, Linux command line shell. Don't worry. And it will connect it to our Kubernetes cluster. There is this tiny icon that opens it in a new window.
So the Cloud Shell is actually provisioning a VM in the backend as well that runs your shell commands on. So that also takes the amount of time it takes to provision a VM behind that.
So while it's provisioning, again, link to the web page with all the examples we are going to do. Please open it. We will copy and paste. The commands are pretty long to type and contain some URLs. So please open this while the shell is starting. Do I have my shell? Come on. Really? OK. Cloud Shell is popular right now. We are still trying to find a VM for you. Please wait. Nice.
So if you are not at this step right now, just please raise your hand, and someone from the side will come and help you get to where you need to be.
Anyway, this is the web page I told you to open. I will zoom it in a bit. It's a complete source of the counter as a service pod. And it's a pretty stupid Golang application. But it contains all the steps we are going to do. Come on, Google, you can do better. Can I connect from my own shell? I do have control. Okay. Luckily, I have my own Kubernetes client installed.
Right, so another way to do this is if you have your own terminal with the gcloud SDK installed, you can actually just go to your own terminal.
I am not logged in.
Sorry?
I am not logged in. I'm logged in as me, not as this crazy.
Jan is not logged in, but if you are logged in, or you can log in as the dev, the test credentials that we gave you, and you can actually run this on your own terminal as well. You just copy-paste that connection command to your own terminal, and that would work.
Is there some anonymous gcloud mode?
gcloud set credentials or something.
Blah, blah, blah. GKX, everything. I don't want to.
You don't want to do that.
Come on. Is it just me or everybody is slow? Sorry? Gcode auf login. Yeah. Oh, I will just def star. E.
So apologies for the Cloud Shell not working right now. What Jan is doing is he is logging into the gcloud SDK on his machine as the dev account that we've given you. So if you have the gcloud SDK installed, you can follow the steps that he's doing right now. If not, please just wait for the Cloud Shell to provision. It will finish eventually.
What?
And if your Cloud Shell is working, then you're good. Just wait for us to get our thing working, and we'll continue on with the tutorial.
It's not really working for me. Still waiting for good. I can try. Still provisioning. And gcloud doesn't really work. No auth provider for GCP. I'm not GCP. Yeah, that worked, but this doesn't work. Good old. No. Okay, plan B. Finally. I do have my shell. So, I have my Google Cloud Shell now connected. I'm not too sure where you are. You have your shells still waiting, just waiting for me. Okay, it was just me. And we will go through the tutorial. So, the first, we will create Cassandra stateful set. Step number 1. copy, paste. We are just applying some YAML file from internet. Don't worry, it's a super safe YAML file. And what did get, it downloaded the YAML file from the internet and gave it to kubecontrol apply. And that created a stateful set. Kube. It created a stateful set, and what by default stateful set does, it creates each replica at a time. So at first it creates Cassandra-O. It creates the PVC, it creates the pod, and waits until it started completely. And after that, it will start Cassandra-1, wait until it's completely started, and then start Cassandra-2. You can configure in the stateful set that you want to run them in parallel, but then it's slightly harder to build a cluster. Because what Cassandra does, it will start the first replica, and all the other replica will connect to Cassandra-O and join its cluster. While it's starting, we can explore some options that kubecontrol gives us, like kubecontrol getPod-W. It enters a wait mode, and we can see all the replicas starting slowly. Or we can try this describe command. We will describe Cassandra-2, for example. Describe pod, because we need to know. We describe pods, and it will list a lot of stuff about the pod, what image we run, what ports are open, what IP address it has, and in the end, there are events. If there was some error, we would see some error in these events. Everything is starting, so that's good. But it's starting for long, so what we can do, oh, this doesn't work. We can check logs, for example, Cassandra-2, and we get logs from the pod. Or if we use -f, it will follow the logs. Well, everything is already started. So, right now we should have 3 Cassandra pods running. They form the cluster, and we have our database. That's the database part. Everybody's here? Everybody has a cluster? No? Yes? I don't see any. I don't hear any feedback. Now we deploy the application. We did step number 2, waiting and using these commands to debug our cluster. But now we apply the second YAML file. Let's create a deployment and service. If I look at the pod, we have now 1 extra pod. That's the application. We just need 1 application. That's fine. And if we look at the service, we get this headless service named Cassandra. It doesn't expose any IP address. It just provides the DNS names for our Cassandra pods. But we have counter as a service of type load balancer, which has cluster internal IP address 10.7.241.38. This is reachable only inside the cluster. So if I had different pods in the cluster, they could use this IP address to reach the service. But it takes some time to get the external IP address. So yeah, now we have it. I have the IP address. Google did some magic and exposed this IP address on the internet. And that's our application. As I've said, this is just counter, and it increases with each reload. There are some debugging information. For example, the IP address of the database server that answered the application query, what query it was, update some counter, how many attempts it got, and how long it was. Each bump basically means we need to update the counter and select the current value. And you can see that the IP addresses of the database servers are changing with each reload. They are free, so we have 2.4, 1.4, and 0.8, and again 2.4. So the client does round robin between the database servers, the database daemons. And that's it. We have our stateful application. That's the StatefulSet with Cassandra. The database is stateful. And then we have a stateless web front end that just does query the database. Right? We are ready for production. And where is the tutorial? Here. So we are at the step 4. We tested the application, used the external IP address from kubecontrol get service. We can also look inside what Cassandra thinks about itself. What we do, we execute kubecontrol exec that execs a command inside Cassandra-O pod, and it executes node2 status. You can imagine something like SSH, but with Kubernetes and container runtime instead of the SSH. So we executed this node2 status, which gives us status of the Cassandra cluster, and Cassandra knows about these 3 replicas. All of them are up and running, and everything works. And the application explicitly asked to store 3 replicas of each counter. So here we can see that each Cassandra pod owns 100% of the data. And what we are going to do, we are going to scale up. Our counter is super popular. Cassandra pods are super busy, and we need to add more. So let's add Cassandra pods. We use kubecontrol scale -- replicas 4. And what are we scaling? We are scaling StatefulSet / Cassandra. What happens? Is that Kubernetes will start Cassandra-3 for us. And it's slowly starting, joining Cassandra cluster, doing some replication, and whatever Cassandra needs. Important is that our application is still running. It's still using 3 replicas. We can use the -v, -w. Well, it's already running. And now we should have 4 IP addresses, 1.6, 1.4, 0.8, 2.4. Yeah, we have 4. What Cassandra thinks about itself is this. We execute the node2 status again, and now Cassandra thinks it has 4 replicas, and each of them owns parts of the database. So Cassandra internally did some reshuffling of the data and spread itself across more nodes. And that's what we want from our database. And now, the fun part, we are going to kill things. For example, well, what happens if one of the paths fails, like it crashes or whatever happens? We just kill it with kubecontrol delete pod Cassandra-1. And what Kubernetes will do, well, it's already dead, and Kubernetes started immediately after the death, started immediately a new Cassandra pod with the same name as before, Cassandra-1, but with a different IP address than before, 2.5, And before it had IP address, 1.6 is missing. And instead of that, we have 2.5 IP address. So pods have different IP addresses whenever they start. What's important for us that the DNS record is still the same. It's still Cassandra-1.service.whatever. So it's important that your clients don't use the IP addresses. They should use the DNS entries because they are stable. IP addresses are not. I didn't show it, but the application survived, and it survived also while the pod was down. And, well, that's basically it. I can scale down back to 3 replicas just to show you what Cassandra does, but this is not really important for the tutorial. We scale back to 3 replicas. Well, it is important because what happens, Kubernetes always kills the last pod in the stateful set. So it killed Cassandra-3. So we have a nice ordered set 0, 1, 2, and 3 is gone. And if we look, what Cassandra thinks about itself is Cassandra thinks it has still 4 replicas. Because what Kubernetes did, it just killed the pod, nothing else. It thinks that this 1.6 pod, it is there, it's still waiting for it to be up. So it's down. And Cassandra did not reshuffle the data. So again, it's important if you scale up or down, you must make sure that the application knows what you are doing. In this case, Cassandra-3 will never come back. So we will execute this magic command, and we will tell Cassandra that this host ID is never coming back, and we will remove it from the cluster. And Cassandra does some magic and reshuffles the data, and so it still keeps 3 replicas of each entry. So if I look back what happened, I can see all the replicas own all the data. So that's basically the tutorial. The things to remember is use DNS names, not IP addresses. And when you scale up or down, you may need to poke the application to tell it that the replica, that there is a new replica, or the replica that just died is never coming back. And back to the slides. How did it work for you? Did you follow, or was it too quick? Any problems? Looks good. Back to the slideshow. So that was Cassandra. You can see Cassandra, it worked pretty well. It scaled up pretty nicely. It scaled down with some manual poking. But I guess you can find use cases where it won't work, but Cassandra will not have enough performance or will perform differently than you would expect. Because all the databases work differently in different conditions. We will look at the other databases and StatefulSet for them. Initially, we thought that we would show MySQL and WordPress during this demo, because that's what everybody knows, everybody uses, everybody knows how to deploy it on bare metal. So let's try it in Kubernetes. And very quickly, we found out that that's not that easy as we thought. It's not even possible, I think. In our Kubernetes documentation, there is this YAML file. Well, I can show it to you because it's enlightening. Here is a YAML file for the StatefulSet. And you can see it contains some crazy shell scripts that do the magic. and form MySQL cluster. And the cluster it forms a cluster where the first replica is read-write, but all the others are read-only. But WordPress needs all the connections read-write. That means it would not scale, basically, for WordPress. You can maybe find a use case where it could scale for you, but in this example, it will create a read-write metric, just the master, and all the others are just slaves. Maybe you can find also a different stateful set for MySQL. I didn't find them, but I didn't try hard enough, I confess. For Postgres, there is a company called Crunchy Data, which provides enterprise support for Postgres. And they also provide a nice YAML files how to run Postgres in stateful sets. They look nice, but we didn't test it. And they also publish an operator that simplifies the deployment. And actually, it looks solid. Maybe it's what you want. We tried Mongo. You can find a couple of stateful sets for Mongo. It looks nice. It's almost like Cassandra. Instead of an operator, it uses a sidecar that does the balancing and all the scaling up, scaling down logic. I found just one glitch, and that was if you connect to Mongo, you need to provide a connection string, connection URI. And in this connection URI, you must specify all the replicas of Mongo. That's fine. In our stateful set, we have stable database name, DNS names. That's fine. But what if I scale up the application? I must add this new pod to this URI. I believe you can do it. It's not hard, but that's something you need to think about. And then there are a bunch of cloud-native databases. Like, I just picked few representatives, but there are many more. And you can find them here on KubeCon. So you can go to the booth area and ask them what the features are, what problems they solve, what problems they don't solve. Because I believe there is no right database. Like, you should learn about all the databases and choose the right one for your use case. Every use case is different. And I'm going to cover some more advanced topics about stateful applications. The first one is the installation part. You saw we installed some crazy YAML files downloaded from the internet. That's usually not what you want. There are two ways how to install applications better on Kubernetes. The first one is Helm, and using Helm charts. It's basically a template of a YAML file. So you just fill in some variables, like your DNS names, whatever, number of replicas you want, storage class you want to use, and this kind of stuff. And it will generate YAML files for you, and it will create them. And that's where Helm actually stops. It just creates the objects and doesn't care about them too much. And the other approach that's being more popular now is operator. Operator is just an application that can run in your clusters. And it will create the application for you, like Cassandra or PostgreSQL, and it will also monitor it. So if something breaks, it can automatically fix it. Again, it depends on the operator. Some of them are very simple and don't do much, but some of them can be pretty smart and fix a lot of things for you. And before you start deploying your application and your databases, you must also think there are some differences to the bare metal world that you are maybe used to. For example, updates happen completely differently in Kubernetes than in the bare metal. And when you are choosing the database or the application, you must think how I'm going to apply updates. StatefulSet supports rolling update. That means it will go from the last replica, Cassandra-2, for example. It will kill it, start a new one with the new version. Then it will go to Cassandra-1, kill it, and start the new version of it. And Cassandra-0, kill it, and start the new version of it. That looks fine if your database can support multiple versions of itself in the same cluster. Maybe they should do, because that's the only way how to update the cluster, but be very careful so you don't run incompatible versions in the same cluster. And StatefulSet can do that very easily. Another thing you should think about before deploying something stateful is the networking. As I showed you, IP addresses are completely random. They change. Only the DNS names are stable. So should the client resolve all DNS name before every connection, before every database query? Or in the case of Cassandra, I found out that it automatically discovers IP addresses of other members of the cluster from the old members. So if one IP address changed, the client discovers it automatically without any configuration, without anything. That's fine. But can your client do that? And the other network-related topic is the network partition. If you have two data centers connected with a cable is broken, you have parts of your database on different networks. They can't talk to each other. So what should happen, and what do you want to happen in your application, actually? Backup. This can behave very differently than in bare metal. Backups are usually easy. You can find some way how to dump your database. It's not that different from bare metal, but how do you restore the backup? Because in Kubernetes, StatefulSet will create the persistent volume claims for you. It will bind them to empty volumes. So how do you populate the data from the backup? Will you dump will you just load the dump? Is it possible? If I have 2 terabytes of dump, how long it will take? Or can I do some manually pre-provisioning of the volumes and get the data from there? You should practice that and test it that your approach really works. And, well, David told you that Kubernetes are just ephemeral. They come and go. They are often killed when a node goes down or some more important pod comes up. So what your database does when a pod dies? And we didn't do any special configuration. So in our case, in our Cassandra, it could happen that all the pods could be on the same node. So if the node goes down, all the pods from Cassandra will go down and your database is down. So you should probably make sure that they spread evenly across the cluster. Kubernetes has a concept for that called anti-affinity. And it can also help you to spread the pods of Cassandra across different data centers or different availability zones. So you should plan ahead. And, well, I hope it's the last one. It's security. Currently, our Cassandra pods were not secure at all. You can connect to it just knowing its IP address. There was no username, password. You can add usernames, password, certificates, or whatever easily. It's not that different from bare metal, but what may be different is that the pods are running on random nodes in the cluster, and you don't know what else runs on the node. And for example, in our case, we have this web application. If somebody hacks the web application, and they can get inside the container, and if they find some security issue, and security issues happen, they can probably escape the container and get to other processes on the machine. And maybe they can get to my database with credit card numbers. Is this what I'm going to risk? Or should I do something better? For example, I can dedicate some nodes just for the database. So all that you should consider before deploying anything stateful. in Kubernetes, because it may behave completely differently than in bare metal case. I believe that's all from us. So do you have any questions? Do you want to add something?
Yeah, just thank you for coming to our StatefulSet tutorial. I just wanted to add that those accounts that we gave you, I think, are active for 24 hours. So if you missed any part of it, or you want to try out some of the extra steps that we did not cover, if you go to that GitHub repository, there are some extra steps. You can try them all out. You can do that for the next day or so. Besides that, we'll be here for questions if you have any, but the main portion of the talk is done. And we are part of SIG storage in Kubernetes. We work on all of the storage related things. We have a mailing list that you can email, bi-weekly meetings. You can join us on our Slack if you're interested in contributing. And here is the contact information for me, David, and Jan as well. Are there any questions in the audience? Yes.
Hi. Are there any use cases where you'd use some sort of stickiness or AR affinity, or is it always an anti-pattern to use that?
We have pod affinity and we have pod anti-affinity. Anti-affinity says that I don't want to run a pod with other pod with this characteristic on the node. And that's what we want in the database case. I don't want to run two database pods on the same node. We have also affinity. I never use that. And that says I want always to run on a node where this pod runs. I can have a driver pod with driver and something that uses the driver, so they want to run on the same node. Maybe that's the use case, but I never use that actually.
Right, and just to add to that, I wouldn't call using affinity an anti-pattern. There are lots of valid reasons why you would want to schedule specific pods to specific nodes or not to specific nodes. Yes.
Session affinity. With the client. So session affinity with the client. What we didn't tell you that all the service object, it does load balancing. That's great, but it also does load balancing based on HTTP cookies. So if I have two pods in the web front end, and then Kubernetes will route my browser just with one of the pods because it's based on HTTP cookies. Does it answer your question?
Are there any other questions?
I think which part of Kubernetes does that, and I think it's the service or load balancer service.
Right, you might have to look into what exact load balancer is being provisioned for you and how that one works. I saw a question over there.
Could you describe what happens when a node fails? What's supposed to happen to the PVs that are attached to that node?
So the question was, what happens to the storage when the node fails?
Storage. You can remember, where is my cloud thingy? You may remember that I scaled the Cassandra up and scaled it down. So I have 3 pods in my cluster, but come on, get PVC. Oh. I still have 4 persistent volume claims. What Kubernetes does, it deletes the pods, but it does not delete the claims. Good. It was a good question, actually. Because StatefulSet are precious, and storage are precious even more. Pods are easy, you can delete them. start the new ones, they are stateless, basically. Kubernetes will never delete the state. It will never delete the persistent volume claim. So if you delete the stateful set, it will delete all the pods, but it will keep the storage around for you. And you must manually delete the claims when you don't need them. Sorry?
Right, the question was, I think, what happens to the storage when the node goes down? And I think it depends on what direction you look at it from. The storage itself, if it's like network attached storage and your node goes down, your storage is still available somewhere else, right? Or it's still available externally. So if you configure your cluster correctly and you bring up your pod, your workload that uses that storage somewhere else, you're actually able to then attach to that network storage again and just continue using it. Does that answer your question?
In our example on Google, the storage is somewhere in the cloud. It's not on the node. So what Google does is just attaches the storage to a different node and starts the pod there. That's easy. In Kubernetes, we also have local storage, where you can use nodes that are attached, that are physically on the nodes. But then, if the node goes down, your storage goes down too. So you should use some storage backend that does some replication or cloud or something like that.
Right, this brings up a really good point that choosing your storage backend is really important, right? Like if for different resiliency needs, you can choose different backends, right? If you use local disk on a node, if that node goes down, you lose access to all of that data, right? But if you're using something like network attached storage or even replicated network attached storage, you're going to have better resiliency guarantees on that. All right, are there any other questions in the audience?
No. It's too far. Good exercise.
Hi. My question is, if you have situation where you have database like master and slave, and you have persistent storage, and do you need to use 2 storage classes for that, or you can use 1 storage class? Because you want to ensure that master always gets the same persistent volume, and the slave always gets another one.
Oof. So you have multiple pods that eventually need to use the same persistent volume? Really? Well, that probably then StatefulSet is not good for you, because it expects a volume for each pod. You can use deployment that will, you have the picture?
I think from what I understand, you want a storage, like you're asking if you should have a storage class for all of the storage for your slave workloads and a different one for your master workloads. Is that your question? So the way you choose how many storage classes you need, it actually depends on the needs of how you group your storage, right? If the masters and the slaves use the same type of storage, I'm assuming each one has its own volume, right? Each replica of your masters and slaves. So if they need the same type of volume, they can use the same storage class. So say they all need SSDs from GCE or something. You would have 1 storage class for that, and your masters and your slaves would all use that 1 storage class. If you want SSDs for your masters, but some other type, maybe like NFS, or you want hard disk for your slaves, then that's when you would have 2 different storage classes, right? Storage class is a concept that binds a class of persistent volumes, a class of storage together. Did that answer your question?
Oh, maybe this
Kinda.
answers your question. You can have multiple pods using the same storage.
No.
If you know?
No, it's like there's master and slave, and basically when a master goes up, want to pick up the same files when it goes down. And same case for slave.
If I can just try to rephrase again, I think, are you asking if when you're workloads go down and they come back up, you want them to use the same underlying storage that they were using before, right? So that's definitely possible with a stateful set. They all have stable naming of the workloads, and so when they come back up, I think they'll just pick up the same storage again from where they left off. Yes, with a stateful set. Okay, one more question over here.
Thanks. Thank you for your talk. Quick question. Is it possible to resize the persistent volume claim? Let's say I created a database with a disk of 10 gigabytes, right? And then I want to grow it to 20. Do I need to do load restore, or is it possible to resize it?
So this is a great question. We're actually currently working on resize functionality. So in Kubernetes, I believe in Kubernetes 1.13, we have resize as offline resize as beta. So this is a thing that you can do right now. Of course, your storage backend has to support it as well. But I believe the way you interact with it is just by changing the size on your PV or PVC. Well, you should look up the documentation for this, but you change the size on it, and if your storage backend supports it, that will just kick off the whole process for resizing.
Yeah.
And another plug is we're actually working on online resize as well. So offline resizes, while your workload is using the PV, you can't resize it. You'll have to bring your workload down first. But currently in Kubernetes, we're working on online resize as well. So if your storage backend supports it and your file system supports it, you'll be able to resize your volumes on the fly.
So in this example, I can resize the PVC from 0 to 5. Really? You don't have it by default? Why? Well, it was allowed. That means the admission plugin is not there, right?
All right. Are there any other questions on the floor? I think Jan is trying to demonstrate resize.
No.
No, he's not.
You have it disabled in your cluster. Yeah, they have it disabled. But you just edit the PVC and that's it.
One short question. I tried to use the StatefulSet with Elasticsearch and use as backend the host mount. And to allow this, I need to make sure that the first instance always lands on the same node, because host mount the data for the first instance is specifically on this node. Is this possible, or do I have to use a more clever backend storage backend?
So the question, I think, was if you're using a stateful set, but you have specifically requirements for your 0th pod for some affinity to some node. So, okay, but not your other pods. So,
I don't know, actually.
Yeah, I think the answer for me as well is I'm not super sure. Yes. Do you want to?
So don't use host path for your production applications for exactly the reason that you mentioned, because you're going to have to take care of actually scheduling the pods. Kubernetes doesn't know that it's going to have to stay sticky to that node that it first gets scheduled to, so that becomes complicated. What you should use instead are persistent local volumes, and persistent local volumes, the scheduler is aware wherever this volume is first scheduled, it will always be rescheduled to the same location automatically. And the caveat there, of course, is that it may, if your node goes down, you're going to lose that storage. So you have to do application level replication. But with your database, you're already going to be able to do that, but the scheduling gets taken care of for you automatically.
Cool. So that was the lead of SIG storage. That's Saad Ali. Any other questions?
To update our database, whether they're like SQL or much simpler, does Kubernetes offer some primitive that beyond what we have in operators? Yeah, like, yeah, schema-wise, or like,
I see. Okay. So the question is, if I want to update my database schema or something to do with my application, I guess, does Kubernetes offer any primitives to help with this update? Is that okay? So yeah, we don't. So Kubernetes schedules the workloads onto nodes. We don't. Like Kubernetes core doesn't really have anything that will deal with your application directly, but we do have primitives that can stop your pods, right? You can stop your containers, you can start them, but I don't think it's going to do that in an application consistent way. You would probably have to deal with your application specifically for that kind of. Yeah, you can use an operator to solve that problem.
Well, you can write your own operator to solve the problem. I don't think you can find any operator already existing for this.
All right, any other questions?
I'm not 100% sure if this was already covered, but my question is if I have some sort of a database, say PostgreSQL or something, and I need to have this running as a database cluster, are there solutions available to get this up and running within a Kubernetes system so that I do not have to create my database cluster outside of my Kubernetes world?
The question being, are there solutions to bring up my database solution inside of Kubernetes? Like as an entire cluster or just inside my cluster? I guess both are very similar. So
solutions.
There are other solutions, right? Like this is not, you won't have a Kubernetes primitive. Like there's not going to be any Kubernetes command that you can call that says bring up my Postgres cluster. But of course there's a very rich ecosystem of solutions that people have built on top of Kubernetes that you can leverage. So we don't have any specific recommendations or suggestions for you, unfortunately.
Don't have. You can try this crunchy data.
Jan has tried this crunchy data, but I don't think we, personally endorse it.
Yeah, I never tried it, but
we've never tried
solid,
it.
like
but you can look into it.
And they provide enterprise support, so you can blame them if it fails.
All right. Any other questions?
No more questions. Then we end up early.
Cool. All right. You guys, we're ending early. Thank you again for coming, and thank you for all your questions.